lecture of today. This is part of the program of 2024 of our network, Latin American Network on Electromagnetic Effects in Strongly Interacting Matter. And today we have the pleasure to have Professor Gabriel Denicol with us. And Gabriel will teach us about hydrodynamic models in heavy ion collisions. This idea came mainly from the discussions in a workshop that was promoted by a few of our members last year, and it took place in Trento. And the idea is that what we're doing, exploring mainly theoretically these electromagnetic effects in strongly interacting matter, could be more connected to observables, in particular observables of heavy ion collisions. So if you want to connect this to phenomenology of heavy ion collisions, one or the main way to do it is via hydrodynamic evolution. So we wanted to start from the beginning, and we invited Gabriel, who's an expert on this topic, to teach us step by step from the beginning. So the idea is to have a lot of discussion, and everybody please feel free to interrupt, and also those who are following the live transmission, you can send me questions or comments by the chat, and then I will open the microphone for you. So also feel free to interrupt. And let me just briefly introduce Gabriel. So Gabriel Denicol, he had his degree in physics from Federal University of Rio de Janeiro, and then he had his master's degree from the same university, and the PhD from the Goethe University in Frankfurt, in Germany. After that, he did postdocs at McGill University and at Brookhaven National Laboratory, the first one in Canada and the second one in the United States. And since 2016, Gabriel is a professor at Fluminense Federal University. He is currently an affiliated member of the Brazilian Academy of Science since 2019. He's editor of Journal of Physics G, and he is very well known in the field. He has published more than 120 publications according to InspireHub with a lot of citations. So thank you very much, Gabriel, for being with us today, and go ahead.
Okay, so thank you, Ana Julia, for the invitation, Gaston as well for the invitation and for the introduction. So, as she said, the goal here is to discuss a little bit about hydrodynamic model of heavy ion collisions in a very basic way. So it's supposed to be understandable for students. And if you guys in particular have any questions, feel free to stop at any moment. This would be very important for this whole lecture. So first, let me tell you what I plan to discuss here. If there is, not only today, but in principle, this should cover both days. So I will start with some motivation, a very general motivation about hydrodynamics and heavy ion collisions. So what is the connection between these two things? And for sure, there is one. Then I will discuss relativistic hydrodynamics itself, the theory, and how it is applied to heavy ion collisions. And I will discuss then two additional features of how we describe heavy ion collisions, which is the initial conditions. So this will be the starting point for our hydrodynamical simulation of heavy ion collisions, and also the final stages of these collisions where we have to discuss how we produce particles from this fluid and how they freeze out, how they reach the detectors, and how these things are connected to things that are measured. So this is the plan, and as I said, I will start from the very beginning. And now it's not working. Move it. Ah, it worked. We'll see now if it's going to jump a lot of slides since I pressed it many times. So this is my motivation. I said very general. I'll start with something very basic. So the main point of our field, or part of our field, is understanding nuclear matter under extreme conditions. Some very basic questions that you can ask about what happens to nuclear matter when we heat it very much. So in particular, we want to understand extreme scenarios, so you can think about temperatures that are larger than the mass of the proton. And then you'd expect that, as happened in our early universe, when temperatures were so large and so extreme that ordinary nuclear matter like protons and neutrons could not exist. You could argue that protons melt in this scenario. And you can ask what happens then. Or in other scenarios, what happens to nuclear matter when we compress it very much, like what happens in neutron stars, when you can, essentially gravitational force squeezes nuclear matter, and you can achieve densities larger than the proton. So you can ask then what happens when we squeeze the proton. So in both of these cases, we are leaving the scenario of conventional nuclear matter to something unconventional, and you can ask what happens then. Maybe I have to stand closer to this. Yes. So in principle, we are not asking anything beyond the standard model of physics. So all of this should be addressed by quantum chromodynamics, which is the fundamental interaction behind the strong force. And it's all given by this Lagrangian here, which is very easy to write down, but extremely difficult to solve. So of course, we can solve it in some scenarios, but in general, it's very difficult to solve it. And so as it happens, so QCD is, of course, a very well-tested theory. It has been tested in various scenarios, in many regimes, but it's not a very well-understood theory. There are many emergent phenomena from this Lagrangian that we only know of because we measure it, we observe it, but they're very difficult to understand from first principles. And so often, if you want to address these issues, you need some experimental guidance. So you need to use experiment to better understand this fundamental interaction. Oops. And here we come to actually this goal of heavy ion collisions, which is connected to this motivation. So of course, the goal of heavy ion collisions is to produce and study QCD matter near local equilibrium. So you want to produce in the lab this hot and dense nuclear matter that in principle existed at the very early stages of our universe. It was very hot and dense, and study it, because we cannot really study it from first principles just yet. And that's where we come to heavy ions. So the fact that we collide heavy ions, it is not really the fact that they're heavy that's important, but the fact that they're large. So you're colliding two large things at very large energy so that you can produce a lot of nuclear matter in a large volume and somehow achieve a thermodynamic limit. So the goal of colliding these big objects is to produce a lot of stuff in a large volume and somehow achieve the thermodynamic limit. And if you do that, then you can actually try to study things like this phase diagram, which is the more formal way to ask the questions that I posed at the very beginning. Like what happens when you increase the temperature, you go in this vertical axis, or when you increase the baryon chemical potential or the density and look for possible phase transitions. So as I said, the goal here, the experiment is not to test QCD, but to understand it. And it's a very different motivation than traditional particle physics, where they want to do collisions and just study one particle or one specific thing. Here we want to study a collective property of matter, like a thermodynamic property. So the goal is really to produce a bunch of stuff and see if it will be a fluid. People who don't understand this think it's a mess, but it's exactly what we want to do. So just to show a nice picture, these are the two experiments that can do this today. One is at in the United States, in New York, the Relativistic Heavy Ion Collider, RHIC. It's exactly at Brookhaven National Lab. It collides gold-gold around 200 GeV per nucleon. And we have, of course, the most famous one, which is the LHC in Europe, which collides lead-lead at 10 times the energy, 5 TeV. In each case, there are some experiments, dedicated experiments that will do heavy ion physics. Of course, the LHC, it does more than heavy ion physics, but heavy ion physics is a part of the program here. And there's one dedicated experiment, at least, that does specifically heavy ion physics. This is another nice picture before we get into the equations. And this is just to show, when we talk about the thermodynamic limit and producing a lot of particles, this is the type of event that is measured at the LHC. Each track here is a charge hadron. And here we have this huge cylindrical detector. So in this event, you have around 10,000 charged particles. And of course, there is this hope that in these collisions, we produce this thermodynamic system that we aim for. Now comes the problem. So of course, if we succeed in this goal, if in fact these heavy ion collisions produce a system that is close to thermodynamic equilibrium, then the following thing will happen. So this is an illustration of what we think happens in a heavy ion collision. So of course, here to the left is before the collision, where we have these ultra-relativistic heavy ions just in collision route. And at some point, they will collide and start producing matter. And we hope for, that if the collision is just has a sufficiently large energy, this matter will reach thermodynamic equilibrium and will just produce a fluid. Now the issue is this fluid here cannot be contained, so we have no technology to just put it in somewhere and just study it. That's just impossible. If we think about it, I mean, we are producing a fluid here that is smaller than the atom, way smaller. So it's way, way smaller than the atom itself. So a lot of people in the daily life think that fluids are made of atoms. So this one is a fluid smaller than the atom. Of course, this is possible because QCD is a very short-range interaction, so you can make macroscopic systems that are very small. But this is an extreme situation. We have no way of just containing this. So what will happen is that this very hot fluid will just expand and cool down again. And what you'll measure at the very end of the experiment is just the particles that are produced at the late stages of the collision when the system is very cold and dilute. So you measure hadrons, leptons produced at the very late stages. And then if you want to study the fluid that is produced at the very beginning, you must somehow reverse engineer these properties. You must understand how what you measure at the end is correlated to what you produced at the very beginning. And that's the heart of this fluid dynamical model. So if you want to really understand things, you have to model the whole collision. And a huge part of it is modeling the expansion of this relativistic fluid. So in this sense, these hydrodynamic models, which is what is illustrated here, are very natural. It doesn't mean they're right, but it's the first thing that you're going to check, right? You want to check if this thing is really happening in a collision, because that's what we want to happen. We want to check this. And if there is a fluid, then we study it. Now, so far, the success of this model is empirical. So what we can do is simply model the whole collision like this, compare to data, and make sure that it's working. And it does work. So empirically, we kind of take this as proof that this thing here is a good illustration of what's really happening there. And of course, the main assumption, I just want to emphasize this, the main assumption of this whole thing is that this system will approach local equilibrium on very small time scales. So right now, we think that around 1 Fermi over C, this somehow equilibrates and becomes a fluid. No one can really explain how this is, actually occurs, but we take it as something empirical. We just try this, and then it works. And so we believe it's true. But yes?
So at first, when it started, you didn't assume this. You didn't assume anything, and you checked that it works if this is true.
No. So we assume this is true. Yeah, we assume that you produce a fluid at some time. Usually this is a free parameter. And then you fit the data. And
you fit the parameter and you find that.
Exactly. But unfortunately, we don't have many control parameters in the sense that we don't have many models which doesn't have a fluid here to check what happens if you don't have a fluid. But usually those few models that exist in this situation, they don't provide a very good description of the data. So far, you just assume this is true and you kind of go with it. So I want to divide this whole thing in like a few pieces. So usually we think about this collision in a very hydrodynamical sense as before hydro, and after hydro. So if you want to kind of construct these models, you have to think about them, or it's convenient to think about them in this way. We divide them in 3 pieces. First one, what happens before hydro. So if you want to model this fluid, you somehow need to understand or model how it reached this fluid state. So you have to describe this initial state physics of initial particle production at the very beginning of the collision, and somehow this pre-equilibrium stage, in which this matter equilibrates or thermalizes and becomes a fluid. This is, of course, extremely difficult. And I would say today it's kind of impossible. Like you'd have to solve QCD and really show that it thermalizes, so it just cannot be done. So it relies a lot on some effective description that we'll discuss later. But I would argue this is the most challenging part of this whole modeling, is initial state physics and this pre-equilibrium stage. It is also at these stages that we know for sure the magnetic fields are very large. So in this initial state and pre-equilibrium phase, we will have large magnetic fields, even though today this is not taken into account in any models. So that's a comment that could be interesting for this audience. At some point, you're going to assume it thermalizes or becomes a fluid, and then you'll try to model the fluid dynamical expansion of this system. Usually, we believe it's a quark gluon plasma that later hydronizes or goes for a phase transition and goes into a hadron gas. And in this is the part that you want to model, and often we also want to understand. We also want to understand this medium that is produced. So its properties like the pressure, the shear and bulk viscosities, any type of charge diffusion. So this is the part that you want to model and study at the same time. And finally, when the system becomes very dilute, so it really expands very quickly, becomes very cold, and then it no longer can be described as a fluid, but there's still some interaction, and you describe it using a transport description of a hadron gas. So this late stage, you describe usually using some kind of hadron resonance gas model in terms of cross-sections and collisions. It's also a very complicated and difficult thing to model with many unknowns. But in principle, if you want to do the whole collision, that's what you have to worry about. In all of these pieces, there are uncertainties, so things that we don't know, or we have to try to model. So in principle, heavy ion collisions, they kind of bring together two very complicated physics. One is non-equilibrium phenomena, and the other one is QCD. So you bring these two things together, and somehow you have to make sense of it. So initial state, the hydro part, and the late hadronic stage, all of these have uncertainties, and people work in each of these pieces of the model sometimes their whole lives. And second, also you have to worry about how to put these pieces together. So if you're really doing a simulation, you have to worry about how to go from this phase and connect to the hydro phase, and then later making the transition to a hadronic phase. This is also not trivial. You may think it's more like a bureaucratic thing, but someone has to do it, right? Someone has to take all of these pieces, plug them together, and solve it. And that's a simulational problem that a lot of people do. So just to end this very initial motivation part, what I want to say is that simulations here are essential to interpret the data and extract information from these experiments. So as I said, you don't really measure the properties of the quark gluon plasma. What you measure are particles produced at the late stages of the collision. And somehow, if you want to make sense of this, you have to do a very complicated reverse engineering task to connect these things. And nowadays, as I said, these models are very complicated, and they include a lot of physics. And even though I started this whole thing, motivating this from the thermodynamic part, trying to understand what the quark gluon plasma is and so on, I think nowadays is more broad, that people just study heavy ion collision themselves as a proxy to develop our understanding of QCD. So some people will study just initial state physics. They don't really care about the QGP or anything. They just want to understand how this thing is produced, and how it thermalizes. And it's also like a complicated task in QCD that will help you understand this interaction in the standard model. So with that, let's go to something more specific. So I want to argue now, so why do we think these models work? So maybe you know this, maybe you don't know this, but as I said, this is empirical. We have no way to prove it theoretically that all of that is happening. We just check that the data agrees with it or suggests it. So I'll briefly discuss why we think these things work. Okay, now it goes. And then we come to this very famous term, which is elliptic flow, or V2. If you are in the field long enough and you do hydrodynamic simulations, you will hear a lot about this V2 here. And it comes from a very simple picture of a heavy ion collision. So here we see what we expect about a collision. This is the transverse plane. The beam is coming in or out of the slide. And this collision has some impact parameter. So the two heavy ions are not completely superposed. And what we expect is that you produce matter in the interaction zone, where these two kind of nuclei intersect. So this red little blob here is where we think we produce a fluid. Now, if you indeed produce a fluid, something very interesting will happen. So the system will be interacting. That's what a fluid will do. And it will accelerate more in the region where it's more compressed. So in this illustration here, in this x direction, you have a large grade of pressure. So you produce a lot of momentum in this direction, and you produce less momentum in this direction. So this interaction will lead to what we call an anisotropy in the momentum distribution. If the system is not interacting, if it's not a fluid, this thing will not happen, or will happen with a smaller magnitude or intensity. So what people immediately measure is the azimuthal momentum distribution of the final state hadrons. So if there was a fluid, this whole thing will have happened over time, and at the late stages, this kind of anisotropy in momentum will be there. So you expect to have a lot more momentum in one direction when compared to another. So if you do this Fourier series of the azimuthal momentum distribution, this picture here implies that this coefficient is large, the second one, V2. So you expect somehow that this V2 will be larger because of this fluid dynamical response to what we call this initial geometry. The Americans will call this a football shape, but we know this is not true. This is not, maybe an almond shape, or in Portuguese, caroço de manga. So, but of course, this whole thing will be connected to centrality. So if the collision is very central, then even if you have a fluid, this shape will be more spherical, and then you have less of an anisotropy. So you expect that this anisotropy will become more significant as you go to more off-central collisions. So this V2 should increase as you go to more peripheral collisions. Yeah, yes. Rugby ball will be also good. Yes. Where? Sorry. Oh, this cyan. Yeah. Sorry. So Gaston asked, what is this cyan? Here, it's just the direction, one of these directions. So you have to fix. Of course, experimentally, you don't know if this shape will be aligned in this way, like with the longer axis in the y direction, and so you always rotate your axis so that this is the case. So this is experimentally, this is cyan is that. It's just kind of this direction where the momentum is larger. In this picture, it's 0. Yeah. So
it's fixed for all your collisions. I mean, you take an average, and then it's fixed for all.
Yeah. So you either.
Event by event. You can just take each event as
Exactly. That's why this cyan is just for that. It's always to have this as a reference direction. Okay? Because event by event, this thing won't be aligned in this way, right? Theoretically, we can align it this way, but event by event, it could be aligned. Okay.
So can you hear me? Those were.
Yeah, we cannot hear you. We cannot hear you when you're asking something.
Okay, but now can you hear better?
Yeah.
Okay, that's good. Now, because it was asked, what is this cyan? And he was answering, and then I asked if cyan is fixed for all the collisions when they take the average, because if you think of it event by event, you could always take it as 0, right?
No, event by event, this direction would just fluctuate from event to event. Because, of course, if you just take heavy ion events and you don't do anything, you just average them over, V2 will be 0 because this. So the other problem is that I'm pointing to the slide, and I guess you guys on Zoom are not seeing my pointer, right? So I apologize for that. So event by event, this elliptical shape will be oriented randomly. In each event, it will be with a given direction. So that's why you always calculate these correlations with respect to the direction where the momentum is greater, for example. That's kind of what this angle is. Otherwise, you just get 0. So in other words, this is like a 2-particle correlation, if you look carefully. But okay, if there are no more questions about this.
Yes. Yes, I mean, not exactly about V2, but I mean, you're motivating. Yeah. You said you're motivating why fluid dynamics work.
Yes.
if it's not fluid dynamics, what could it be? I mean, I don't see any other possibility.
No, I mean, it could just be some non-equilibrium system. So you can produce a bunch of particles. They may have a few collisions, but maybe they don't interact enough to produce a fluid, right? That's a possibility. If that's the case, usually something like this here could still happen because there is some interaction. But the thing is, for this kind of response to be large enough, you would need the fluid. So at the end of the day, what I'll show is that this V2 will be actually large and compatible with a fluid dynamic calculation with a small viscosity. And that's very difficult to get from like other non-hydrodynamic models, which would be like a large viscosity limit of this. But I'm going to get there.
Okay.
So you are going to define what you mean by a fluid.
Yeah.
At some point, yeah, very loosely.
Yeah, Alejandra Ayala said, event by event, you need to find cyan. This is called the direction of the reaction plane, and it has to be experimentally determined.
Yeah, it's the event plane. Theoretically, we know it exactly, right? Experimentally, they have to find it. So here's just to say that, of course, we don't measure the centrality of these collisions. It's impossible. But what you measure is the number of particles that are produced, and there's a big correlation between the final state multiplicity and the centrality. So we expect that the events with more particles produced are the most central collisions, the ones with a smaller impact parameter, and the ones with less particle produced are the ones which have a larger impact parameter. So instead of talking about impact parameter, we'll just talk about centrality as an equivalent measure of this thing. And that's why you end up plotting things like this. So this is this Vn coefficient, so V2, V3, and V4, as a function of the centrality percentile, which is to the left means the most central collisions, and to the right, the most peripheral ones, so the ones which have less particles produced. And you see indeed that this V2, which is this red curve, increases with centrality, which is exactly what you'd expect of a fluid, of an interacting system. So the more peripheral, the larger the momentum anisotropy becomes. And it's actually very compatible with a fluid dynamic calculation with this viscosity here. So the curves are the results of a hydrodynamical simulation which has all the steps that I illustrated before with a fluid with a very small viscosity. In this case, you have more than just V2. You have all the Fourier coefficients, V2, V3, V4, because when I talked about the system that you produce in heavy ion collisions, of course, there was a simplified scenario. I just drew a perfect elliptical shape, but some fluctuations would just render this shape a little bit more smeared. And then you have also V2, V3, and V4, and V5 coefficients. And all of them are well described by these fluid dynamical models. And then you get something that you want, which is for this specific value of viscosity. So then you extract something. Here is just a very old calculation which shows that this can be indeed extracted. So now it's a theoretical thing. So the black points are the data from RIC, the Phobos collaboration. And now it's not plotted with respect to centrality, but participants. So now to the right, we have the most central collisions, and we go to the left and have the most peripheral collisions. And we see several curves here, which are fluid dynamical simulations of the collision with different values of shear viscosity, for example. And you see that this observable depends a lot on the viscosity. On a very, let's say, intuitive way, the smaller the viscosity, the stronger is the response. The larger is the V2, because you have a perfect fluid, you have a stronger response to the gradient of pressure. While as you increase the viscosity fights against this and reduces this response. And usually you can find some ideal value of V2 to fit the data, right? Now, if you don't put a fluid here, usually you'd get models with a much smaller value of elliptic flow. So if you just run models like URKMD, which has no fluid, no QGP, this V2 is never large enough compared to what you measure. So that's kind of the thing that people can check. Even though I should say this has never been checked with a lot of precision. There are not many models nowadays that don't have a fluid, which is, I think, a problem sometimes. We don't have a good baseline to compare. And nowadays, there's a very big deal about systematic model-to-data comparison. So people are, back in the day, this year just an eyeball fit. So people run the hydro, and they'll just fit by eyeball, just by visually checking which one is better. Nowadays, it's done more seriously by using Bayesian analysis and and global fits. And you can get curves like this about this is the bulk viscosity, and this is the shear viscosity of QCD matter extracted from, now with a temperature dependence. Different curves are different models here. And you can extract like a bulk viscosity and a shear viscosity from data by the simulations. And this here is just an example of several observables and how these simulations do. So particle multiplicity, mean PT, V2, V3 is all here. And these hydrodynamic models pretty much can describe a huge fraction of it with a reasonable precision. But coming back to this one, this here is the kind of thing that we get from heavy ion collisions that usually get the attention of pretty much everyone. So this here is a modern version of this very famous result that the shear viscosity of the QGP is very small. So it's roughly around 0.1 if you normalize it by the entropy density. Of course, it's not exactly 0.1. It has a temperature dependence. Extracting this dependence is one of the goals, I guess, of these simulations. But it's extremely small, and people have a very difficult time understanding from QCD how can it be that small. And there are a lot of conjectures and people thinking about this problem. To the left, there's a different problem that people don't think as much, but is equally important, which is the bulk viscosity is actually much larger than expected. A lot of people thought it would be just 0, because QCD is almost conformal. But what you get from experiments is actually very large values of bulk viscosity, almost 10,000 times larger than what you think about extrapolating PQCD results. So this is a challenge, understanding why the bulk can be so large and why the shear is so small. We know neither of these things. Oh, this one, you know why it goes to 0 here and there? Also, Gaston asked why the bulk viscosity has a peak, essentially, why it should go to 0 to the left and go to 0 to the right. So at very large temperatures, I mean, this we know. So when you go to very large temperature, QCD is conformal, and the bulk is 0. So the thing has to go to 0 at very large temperatures. This much is known. And when you go to small temperatures, you kind of approach the non-relativistic limit, where the bulk is also 0 for gases. So usually for dilute gases of point-like particles, the bulk is 0. I can tomorrow if you want to understand the... Yeah, turn it on.
And you are going to explain everything for us, right?
Yes, this I can cover tomorrow.
Okay,
Like,
good.
what do these things kind of mean, right? To just finalize this part of this presentation, I just want to give you 2 additional signatures that we have a medium there that have nothing to do with these fluid dynamical models. They are additional signatures that indicate we have a medium, besides these collective flow arguments I just shown, which are already very compelling. So one is, essentially we see a thermal photon signal in these collisions, so you can measure direct photons, which are essentially all the photons produced except those that come from hadronic decays. And you can, this is the points measured here. And the curves are just predictions from pure QCD, just what we call the hard photons produced at the very beginning of the collision. You can see that at high PT, these match exactly what is measured. But as you go to low PT, low transverse momentum, there's an excess of photons produced. And these are interpreted as thermal radiation. And actually, hydro models can describe this reasonably well. So it appears that there is some signals of thermal radiation in this collision, so something hot is there. And the other great signal is jet quenching. So things like this, where you measure like one peak of the jet, but you don't measure the other. You expect like a back-to-back jet, but one is just either kind of absorbed by the medium. So this together with this collective flow arguments are very strong suggestions that we are producing a hot and dense medium in these collisions. Right? It's very hard to explain this with any other model. Now, I should say one thing, though, that there is a question, which maybe I'll come back at the end of this lecture, about having a medium or a fluid in smaller systems like proton-lead or even proton-proton collisions. One's advantage of these collisions is that you cannot really measure these things very well. So we measure the flow. So all this V2 we see in small systems, but this is way harder to see. Jet quenching and thermal photons are just way harder to measure. So we're always missing these kind of signals, even though we try very hard. Okay, so now let's try to learn something. So now let's go to some pieces of these collisions and just understand a little bit the theory behind it. So now I'll start this discussion with, of course, the hydrodynamic part. So we'll discuss here relativistic hydrodynamics with some concepts and problems, not only for heavy ion collisions, but in general, but also, of course, with a focus to heavy ion collisions. So here I should mention one thing first, is that in this fluid stage of the simulation, we model the QGP and the hadron gas as a fluid. So what happens here is that you initially produce something that is a quark gluon plasma, at least the temperature is high enough to be a quark gluon plasma. This thing will cool down, it will go through a phase transition or crossover, will become a fluid made of hadrons, and all of that will be described with fluid dynamics. So in other words, the phase transition occurs in the fluid dynamical regime. And that's why it becomes so simple. So we describe this complicated phase transition from quark gluon plasma to a hadron gas just through thermodynamics, how pressure changes, how the shear viscosity changes. That's how we model it. So we shouldn't confuse that, hadronization and freeze-out are the same thing. They're not. So in principle, our goal is to describe this whole thing here from the QGP to the hadron gas. Now, what is hydrodynamics? So that's where we should start. And this kind of helps us to understand why we can apply to heavy ion collision. So if you want to understand the applicability of hydrodynamics to a heavy ion collision, you first have to understand what hydrodynamics is, or what we think it is. Here I give you the usual answer. So of course, it's a macroscopic theory or effective theory, which describes some system over large distances compared to some microscopic scale. So for a gas, this would be the mean free path. So you're usually thinking that you're observing some gas over distances way larger than the mean free path of that system. So we demand some kind of separation of scales where this macroscopic scale where I observe the system and this microscopic scale, little l, they should be widely separated. We expect this small l over the large L to be much, much more than 1. For fluids like water, this is really true. Like usually it's 10 to minus 8 or something. It's really, there is a wide range of separation. For heavy ion collisions, this is usually not true. I'll tell you from the start.
So what is the typical number?
In a heavy ion collision?
Yeah, 5, 2?
Of course, it varies, but at best, usually it's 0.1. So there is a regime, there is a part in heavy ion collisions.
Kn is 0.1.
Yeah, let's say at some point. But because the issue is, Kn varies with time, along the. So there are regions where this Knudsen number is, let's say, 0.1, which would be large for water. So 0.1 for water is already almost leaving the, and then it can reach like order 1 at the late stages. So it's not that small. It's also not that large, at least where we solve it. And this explains why so I don't know if you guys know about this problem of small system, but I keep quoting it. This is why for us it's this big surprise where you have lead, and we apply hydrodynamics to that system, and we do proton lead, and then we're so scared of applying, even though we don't change the size by that much, right? If you have a swimming pool and you describe the water with hydro, if you take a cup of water, no one expects that it won't work anymore because it's just a cup of water. This is why for a swimming pool, hydro is way beyond this, it's very safely under its domain of applicability. Right? For heavy ion collision, we may be borderline. And I guess that's why we have to worry about going to smaller systems. But this is something that we always have to worry about. We apply hydro, right? But we are not, let's say, naive to believe in it unconditionally or just beyond where it should work, right? We should always know its limitations. And in heavy ion collisions, we are pushing it. Even in heavy ion collision, we are pushing it because we don't have the separation of scales as we usually do for fluids. I will later explain why we're very lucky that this works, but soon enough. Let me start with the most basic theory of hydro. This is ideal fluid dynamics, which is based on very fundamental principles. So if you have an ideal fluid, usually you describe it using conservation laws. So here, for example, you have the conservation of energy and momentum, which is a fundamental equation in physics, of course. It's always true, regardless if you have hydro or not. And conservation of charge, which for heavy ion collisions usually we think about three charges: strangeness, electric charge, and baryon number. In very high energy collisions, we neglect them all. We just say they're all locally zero. But in principle, they are there. And as you go to smaller energy collisions, they're going to become more important. In ideal fluids, you assume that the system is in local thermodynamic equilibrium, which means that if you take every little fluid element, every piece of a fluid, that this system, when you go to its local rest frame, when you go to the frame where the velocity is zero, these tensors, T mu nu and the net charge current, will have the form of an equilibrium system. So in this local rest frame of each fluid element, when the velocity is zero, T mu nu will just be diagonal and given by the energy density and the pressure, with the pressure satisfying the equation of state. So the pressure is given as a function of energy and net charge, energy density and net charge density. And the particle current will just have the of a global equilibrium system. If you go to the lab frame, this will imply that your currents will have this kind of form. So your net charge current will just be proportional to the velocity field, with n being the net charge density. And your T mu nu will just have this very typical form, where this delta mu nu is a projection operator. It just is a second rank tensor that is orthogonal to the for velocity. So this here is a very general decomposition. And if you're careful enough, I mean, if you play this counting game, you see that you have exactly 7 equations. If you have 3 charges, you have 4 equations for energy momentum conservation plus 3 equations, 1 for each conserved charge. So you have a total of 7 equations. And if you count here, you have also a total of 7 fields. You have the energy density, the 3 components of the velocity, and let's say 3 conserved charges. So also you have 7 fields, assuming that, of course, the pressure is given by these fields. So the pressure is just given by an equation of state. And so that's all that you need to solve it. So these equations are closed. You can just solve it. And the only thing that will tell you about the fluid is the equation of state. So here's a more typical form of these ideal hydro equations. The first 2 are just the energy momentum conservation projected into the direction of the velocity and a direction orthogonal to the velocity. The second equation here, if you recall, non-relativistic hydro is just the Euler equation. It's a relativistic version of the Euler equation. It's very similar. But those are the equations that you have to solve. And the only thing that tells you about the fluid is the equation of state. So this function pressure as a function of energy and net charge density is what will give you the difference between water and QGP, right? That's all, nothing more. It's just the pressure. Below here, I just kind of give you some notation. So this A dot is the co-moving derivative in the local rest frame, where U mu is 1, 0, 0, 0, is just a time derivative. This is a space-like gradient, so it's just in the local rest frame is the usual space gradient that we know. And this theta is the expansion rate. It has to do with the forward divergence of the velocity. It's usually positive if the system is expanding, and negative if it's being compressed. And if you want to solve this, of course, you need to provide initial conditions for the energy density, the net charge density, and the velocity. So you have to know these things. Once you provide these initial conditions, you can just solve this. For a very long time, this is the kind of theory that was applied to heavy ion collisions. So for many years, the coagulum plasma was just assumed to be an ideal fluid with some equation of state, and you just solve it. And those were the good old days. Now, in this case, nowadays, this is not the case always, right? But nowadays, part of this problem, of course, is known. So the QCD, the equation of state for QCD, at least a 0 biochemical potential, was calculated from lattice QCD. So this is no longer an open problem per se. It's known. We don't have to extract it from the data, since they calculated from first principles. So we just use it. There's a non-trivial bit here where this kind of first principle calculation shows as a crossover. It's not a real phase transition. And below, let's say 150 MeV, it really matches a gas of hadrons and resonances. So these are things that are just known nowadays, and you don't have to worry about extracting them anymore. To be fair, I mean, even when people run hydro models, ideal hydro models, and try to extract the phase transition, this kind of pressure, they never succeeded, right? Until this calculation, this first principle calculation, people thought it was a first order phase transition. And that's the thing they put into the models and so on. But that was just incorrect. If you go at finite chemical potential, then of course that's an open problem. Then what they can calculate from first principles are usually these Taylor expansions of the pressure, let's say, around small chemical potential. As far as I know, they can calculate this series up to fourth order or a little bit more than that. So you don't really have access to the pressure in the whole finite density regime. And people then have to model these unknowns in some way. And in particular, there's this big question about a critical point. So whether this kind of pressure will have at some finite chemical potential, some critical point where the phase transition goes from a crossover to a first order phase transition. And this to this day is not known, but I think it's one of the biggest questions in the field. So this is just to say that nowadays people are coming back to the problem of also trying to extract the thermodynamics of QCD. But at mu equals 0, this is not a problem, and people just focus on the viscous part, the transport part. Okay, so now we want to add dissipation to this fluid, right? Because in principle, there are no ideal fluids. All fluids must have some level of dissipation. For the QGP, people thought it was very small to the point where it could be neglected, but nowadays we know better. It's certainly small, but it cannot be neglected in the simulations. They provide a visible effect on the data. So the way that we do this, of course, is the first part, of course, we don't change. Conservation laws, as I said, I mean, they're always true. Energy momentum will be conserved and satisfy this equation regardless if you are in the fluid regime or not. So this is always true. What will change is just the form of these dissipative currents. So before, they were fixed by this assumption of local thermodynamic equilibrium. Now they can be, their general form can be a little bit more complicated. So what people do, what pretty much everyone does, is think about dissipative terms as corrections to the ideal or to the perfect fluid currents. So here the perfect fluid currents are the first term for the net, for the 4-particle current, and the first 2 terms for the T mu. And then you just add all the other possible contributions that you could have due to dissipation. For the net charge current is just some diffusion current. And for the T mu, you can have all these terms which are underlined in red. Note that I also underlined the pressure because now I can no longer assume that the pressure, this isotropic pressure, is just given by an equation of state. So in principle, even this guy could have non-equilibrium corrections. Now the thing is, these dissipative corrections, they kind of mess up everything that we did before, including what we mean by the equilibrium terms. So the first thing that you have to do when you actually add these corrections is you have to redefine what you mean by equilibrium. And that's a very subtle point. So first, we should think about ideal fluids. So for ideal fluids, this was all very natural. The flow velocity of your fluid was defined by this kind of local rest frame where you have no energy, current, and net charge current. So where the system looks like a system in global equilibrium. While energy and net charge density, they are just purely thermal. So you can calculate them in terms of a temperature and chemical potential. So this is what happens for an ideal fluid. For viscous fluids, the first assumption is just not possible anymore. So in principle, you cannot find any frame where there's no energy current and charge current simultaneously. That's just impossible. So this definition of the velocity field doesn't hold anymore. And here you can also worry about this assumption where you say that the energy density in the local rest frame and the net charge density are just given in terms of temperature, chemical potential. You have to ask yourself if that is really true at this point. So this procedure is called a matching condition or a matching procedure, where essentially we introduce some reference equilibrium state, and we just say, we just impose that all these quantities, your net charge density, your energy density, and your isotropic pressure, they are given by some equilibrium term, and some non-equilibrium term, all of them. The pressure as well is some thermodynamic pressure plus a correction. So you just say that. And then you have to define what are this chemical potential, this temperature. Here's the inverse temperature. And this alpha is mu over T, is a thermal potential. So you have to define what alpha, beta, and nu mu are. So you have to say, what is your equilibrium state, right? And here you actually have more than one choice. You have infinitely many choices, actually. But there are two very famous ones, right? One by Landau and another one by Eckert. Both Landau and Eckert agree that they wanted to define your equilibrium state just by imposing that this correction to net charge density and energy density are just zero. So in other words, what you're saying is that your temperature and chemical potential are determined by the total N and the total epsilon. You just invert them. So you're just saying that all your internal energy is thermal and all your net charge density is just thermal. There are no delta N's or delta epsilons. This is a condition. We impose it. So you just fix them to zero. And then Landau and Eckert disagree on how to define the velocity. So Landau chose the velocity as an eigenvector of T mu. So in other words, his velocity field is just following energy. He's just following energy. And this means that this current h mu, which is the energy diffusion, is just zero. While Eckert thought it would be much better to follow net charge. So he just defined the velocity from this condition here. So there's no net charge diffusion. The velocity just points in the same direction as the net charge current. For an ideal fluid, as I said, these two things hold simultaneously. They are true simultaneously. For a viscous fluid, they just thought it would, good to just pick one of them. But again, in principle, you can just define anything that you want. Even though I should say it's very difficult to think of any other conditions beside these ones. It's very hard to find other matching conditions than these two. For heavy ion collisions, we like a lot this Landau picture, for the simple reason that we usually cannot apply the Eckert picture. So if you go to very, very high energies, your net charge current is essentially zero everywhere, because the number of particles is essentially the same as the number of antiparticles. So this N mu is just zero, and you cannot just follow zero. It's just impossible to define this velocity. So in heavy ions, we always use a Landau picture, and pretty much every single simulation that you have seen in heavy ion collisions is using this Landau picture. In astrophysics, they really like the Eckert picture. There, of course, stars are just made of matter, and you can really define a baryon number current, and you can easily define a velocity from that. So in astrophysics, people are more towards this Eckert picture. So this is the first thing that you do. You have to pick one of these two pictures or some other picture. Here, I'm going to follow the Landau picture for the rest of this lecture. So let's just say you do that. Then this will be the form of T mu. So there was one term that just disappeared. So you have just two dissipative corrections for T mu. This bulk viscous pressure, which is a correction to the thermodynamic pressure due to dissipation. And this shear stress tensor pi mu, which is another type of contribution, which is some kind of anisotropic pressure term that will, so both these terms are off equilibrium corrections. And here we can have this net charge diffusion for current. Since in the Landau picture, this net charge current does not have to follow the velocity. There could be some additional diffusion term. So this is how these things look like. And then you have to worry about additional equations of motion. So for an ideal fluid, all of these currents were just set to zero. And the conservation laws were enough to just solve the problem, to evolve this fluid. But now you will need equations for this guy, for pi mu, and for the net charge diffusion current. You have to find something. So how do you do it? Let me show the example by Landau. So Landau did the following thing. So that's what he did in his book. And he thought it was so simple, he didn't bother to write a paper. So he just wrote a chapter of his book and left it there. So you can still read it. Yes?
I have a question by Malena. She said, so the Eckert picture should be used if you go to lower energy collision energy, where mu is larger. Is there a characteristic square of S below which we should change to Eckert picture? Yeah,
so that's true. At the lower collision energies, then you probably have a net baryon current that you could maybe use to define a velocity field, but it's still very risky to do it. I mean, like if there are some fluctuations where it could still be zero in some wide domain, then your velocity field would just be undefined. So for heavy ion collisions, I would recommend not using the Eckert picture, even though at lower energies it could be more viable. So I don't know. She asked for a possible collision energy where where you could use the Eckert picture. I would know the number, but it has to be very small, very small. Okay. So I don't know if yeah.
Small that is not currently found in any actual
There are so many. So
experiment.
as you go to low collision energy, there are so many problems that could appear. One of them is that people start using like a two-fluid approach, and it can become way more complicated than just changing the picture. So I think you have to worry about other stuff. But I have to say there is a new fluid dynamical framework by Jorge Noronha and collaborators where, and I just quote this as an interesting fact, where both of these pictures are forbidden. So that's why people are more interested nowadays about these kind of matching conditions, because these two were thought about very standard pictures, like very intuitive. But in some hydrodynamical frameworks, they are both forbidden, and you have to think about other stuff. I'm not going to comment about this during these lectures, but people are thinking a lot about these matching conditions nowadays. But one thing that I forgot to comment is, and it has to do with this definition here. So you can think about why this here is a choice, right? So can we really pick an equilibrium state like this, like you're just buying fruit at the supermarket? I want this one or that one. So the reason for this is that actually we have to remember about this is a fictitious equilibrium state, in the sense that it never really existed in the evolution of the fluid. What we have for the fluid is the two currents, which are off equilibrium. And we're just imagining that for this off equilibrium current, there is some nearby equilibrium state where we can expand around it. But this equilibrium state never really exists throughout the dynamics of the fluid. That's the important part. You can really choose more than one neighboring equilibrium state to start this kind of expansion here. So it really is a choice. But since this expansion will be truncated, this choice will affect your result, your answer. Okay, so here I come to Landau. So Landau did the following. Yes. We always assume that they are small. Or let's say, if we divide the system like we did here, where we have some equilibrium part and some non-equilibrium part, of course, in our minds, this off-equilibrium part is small. That's what justifies what we're going to do in the following. But in real life, it's not always true. So that's the problem. And by real life, I mean heavy ion collisions. So in heavy ion collisions, these corrections are not always small, but then we're just going to apply it anyway.
But you still do it.
We still do it. We're not going to stop. Yeah.
And hope for the best.
Yes, yes. We always do it. But the important thing is to know that you're doing it, right? It's bad when you're doing something wrong, but you don't know that you're doing something wrong. Then you're just an ignorant. But when you do something wrong, yeah. When you do something wrong and you know it, then at least, you know that you're just pushing your model beyond its domain of applicability, and you're doing it for a reason, right? So just know that, no, these things have limitations, and this is one of them. So what did Landau do? So Landau, he wanted to derive like these additional equations that would close the fluid dynamical equations. So his starting point was the first equation in the slide. So he calculated the 4 divergence of the entropy current, of the equilibrium entropy current. So S here is the entropy density, U mu is the 4 velocity. So this is the 4 divergence of this equilibrium entropy current. And he found that it's equal to all of that here. So this is an exact result. And of course, if you are in an ideal fluid, the mu T mu is 0. So the 0 means it's just the equilibrium part of T mu. So if you're in an ideal fluid, this is 0. The second term is 0. Entropy is conserved. It's not changing. The total entropy is conserved. So he just took this equation up here and rearranged it in this way, right? And there's some notation down here. I'm using, again, this theta as the expansion rate. It appears as the second term on the right-hand side. There's the bulk viscous pressure times the expansion rate. And sigma mu is the shear tensor, which has to do with deformation of the fluid element. So this theta here, the expansion rate, has to do with change of volume. So if this guy is positive, the volume is increasing. If this guy is negative, the volume is decreasing. while the sigma mu has to do with not changes in volume, but in changes of, in deformation of the fluid element. This guy usually indicates the fluid element is changing its shape. And it appears on the last term on the right-hand side. Yes? No, yeah. So sigma mu, we usually call shear tensor. This pi mu is the shear stress tensor. So they are in principle different things. This pi mu is the guy that was in T mu itself. It's a part of T mu. So this pi mu and this capital pi here, they are off equilibrium parts of T mu. While this theta and this small sigma mu, they are just gradients of velocity, different combinations of grades of velocity. So Landau just rearranged the first equation this way here, and he proposes very intuitive interpretation. He just said, okay, the term on the left-hand side now, this is the entropy forecurrent of my non-equilibrium fluid. So it has an equilibrium part, SU mu, plus some non-equilibrium correction due to net charge diffusion. And then the right-hand side, he interpreted as entropy production. Of course, if this is the entropy forecurrent, its for divergence would be the entropy production. So all of this here is entropy production. And then he proposed that from the second law of thermodynamics, all of this guy here should be positive definite. So our system can never, the entropy should always increase. So all of these terms here on the right-hand side, they must lead to a positive definite value. And this leads to this solution down here. So Landau just said, okay, if I take my capital pi and say it's minus zeta times theta, and the net charge diffusion current as something proportional to the gradient of the thermal potential, and pi mu as proportional to sigma mu, this guy up here will always be positive. And the second law of thermodynamics will always be respected, right? As long as these three coefficients here are always positive. These guys are famous. So this zeta is the bulk viscosity, this eta is the shear viscosity, and this kappa would be the net charge diffusion coefficient. Two of these guys I already showed to you in plots of people extract them from heavy ion collisions. Yes?
This is a particular choice.
Yes, that would lead that this guy is always positive definite. So this is the only choice, which is first order ingredients, that would give this answer. You can correct these things, but then you have to assume higher order gradients. And then there's this underlying assumption that these are just small or subleading terms. So this here guarantees that your fluid will respect this conservation, this entropy production law in any circumstances. So what you want is that any fluid anywhere in any situation will not violate this law. So this is exactly the relativistic counterpart on Navier-Stokes theory. Sometimes we call it first order theory because the answer is first order ingredients. So they're all linear in the gradient of velocity, in the gradient of thermal potential, and the sigma mu is also a gradient of velocity. And you can correct these guys if you want, but we always assume that the gradients are small, and so we believe this term should be subleading. So this is what Landau did, right? Do you have any more questions, or are you still digesting this?
Yeah, digesting. Because, I mean, also you're...
Oops. Means we have to stop, or no?
No, sorry.
Go ahead. Can I go ahead? Okay, good. So this here is exactly what people also do in the non-relativistic setting. So it's very similar to Navier-Stokes theory in general. So just as some intuition, we have then these three constitutive relations. We just relate these dissipative currents, that is, the guys that appear in T mu, with gradients of velocity or gradients of temperature and chemical potential. This guy here, which has to do with the shear viscosity, has to do with resistance to deformation. So every time you try to deform your fluid, its shape, it will produce the shear tensor and then also produce some shear stress tensor. So it will lead to some entropy production or heat production. When your system is, so the bulk viscosity is some resistance to expansion. So if you try to change your volume very fast, then this guy will become large and you also produce entropy and heat. And this guy is just diffusion as usual. Right? So these are the three fundamental equations here. And these coefficients, eta, zeta, and kappa, they are additional properties of your fluid. So for an ideal fluid, you just need one thing, which was the pressure, the equation of state. now we have 3 additional properties that tell you something about your system. This eta essentially tells you how sticky it is. This bulk has to do with some internal degrees of freedom. I'll come back to that tomorrow. And this kappa is how easy it is to diffuse something in your medium. So they tell you something. So very elegant, very beautiful, but also completely wrong, right? So these equations, they look very reasonable. They are essentially similar to their non-relativistic counterpart, but they have intrinsic problems that Landau did not notice at the time, and a lot of people didn't notice. So the problem is that these equations, they violate causality, and they display physical instability. So these equations, the global equilibrium state is unstable. If you perturb your equilibrium, it just blows up. That's, of course, unphysical. So in this sense, even though this is very simple to write down, in practice, you can never really use it, I mean, to simulate anything. And this is the reason why it took so long to add dissipation to heavy ion collision models, is that you're just forbidden to use this very natural theory. So you have to use something else, right? To give you a hint about this problem, so why do we have a problem with the relativistic Navier-Stokes theory and we don't have a problem for the non-relativistic one? So you can think, so here's just some intuition, some finger physics, right? So let's just say large wave numbers, essentially all the dispersion relations from the relativistic Navier-Stokes theory and also the non-relativistic one, they look like something from a diffusion equation. So the omega is essentially I times k squared, and d would just be some transport coefficient. So for those who forgot, this is the diffusion equation. It's something like this. And it's known to be a causal. So when you have the diffusion equation, as happens to Navier-Stokes theory, you are allowed to have perturbations that travel faster than light. Usually it's worse. They travel with infinite speed. So not that they have a velocity that is above the light velocity, but it's infinite. But anyway, this kind of dispersion relation appears a lot in this kind of Navier-Stokes theory or the diffusion equation. Now, if you are in a relativistic case, let's just say you perform a 1D Lorentz boost. So something like this. So you make a boost, and then your omega and k, they'll kind of mix up, right? You mix the time part with the spatial part due to this boost. And then if you look at this equation in this new frame, you just rewrite this diffusion dispersion relation in this boosted frame in terms of omega prime and kappa prime, it will become something like this, which is something very interesting. So for example, because of this Lorentz boost, this k square term will kind of mix omega and k. And this linear dispersion relation in frequency, once you boost it, will become quadratic in frequency. So you have now 2 solutions. And that's already very bad, right? So in one frame, you have kind of one solution, but to change the frame, now you have 2. That's very strange. And what you see is that the second solution is intrinsically unstable. It has the wrong sign here. So in my convention, at least, this positive sign indicates that these perturbations decay with time. With this sign here, you have that they increase with time. So if you go to a moving frame and you perturb like your Navier-Stokes fluid, it will always blow up because these modes will appear. And there's no way around it, right, for this theory. So this theory is just bad, and you cannot use it. So how do we fix it? Yeah? So you mean we have to use a relativistic, yeah. So he said that the expansion with the speed of light for the QGP, I guess, or... Yeah, there's no way out. So there's no way out. Even though some people try to argue there is a way out, but here, there's really nothing you can do. And again, no one has ever solved this, as I said, because it's impossible. Unless, of course, using symmetry solutions. So there's actually one example where this Navier-Stokes theory was solved. It's called Gupsa flow. And it was only solved because of some very special symmetry where you could determine your velocity just by the symmetry of the problem. And when you solve Navier-Stokes, for example, in this Gupsa solution, you find that negative temperatures appear. So you find these very strange and physical features of the solution. So anyway, Navier-Stokes, bad, right? So now, how do we fix this? In principle, I mean, some of you may be puzzled because from the way I argued, it looks like it was a very general thing. So Navier-Stokes theory or Landau theory was based on conservation laws and the second law of thermodynamics, two very fundamental physical principles. So it's not like, it doesn't look like you have a way out, but actually you do. And what Israel and Stewart argued is that Landau's identification of the non-equilibrium entropy was incorrect. It was not the most general possible entropy. And they argued the following thing, that in principle, if you're close enough to equilibrium, they assumed your entropy for current is a function of the equilibrium variables plus the T mu dissipative currents. So here, the bulk viscous pressure, pi mu, and something from the net charge diffusion. And then what they did is they assumed that, and here comes this assumption, that these dissipative pressures are small. So they expanded this equilibrium, this non-equilibrium entropy for current around equilibrium. And they got something like this here on the middle of the slide. So this S0 mu is the equilibrium component. Minus alpha 0 n mu is what Landau obtained. So it would be like a term linear in the dissipative currents. But Israel should argue that we should also put, for instance, this Q mu would be all the possible second order terms, which are quadratic in these dissipative currents. So right here, I write all the possible contributions, where delta 0, delta 1, delta 2, and gamma 0, gamma 1 are just thermodynamic functions. So this is the most general thing you can get. And of course, Israel Stewart, they stopped the second order. You could, in principle, keep this expansion going, but let's stop the second order. And what they showed, and I will show it to you here, is that if you stop a second order, if you just add these additional terms, that by itself will fix your problem. So now, of course, the entropy for current is very different than before. So before, it was just the first three terms, which is what Landau calculated. But Israel should argue, okay, now we have to also add this new term, d mu q mu, which comes from all of these new terms that were added to the entropy for current. And if you do that, you can believe me that the answer will be something like this. So a lot of terms, right? So now the entropy for, production is all of this garbage on the right, all of this stuff here. But I already wrote you in a very convenient form. So if you look carefully, we can still find a solution which is positive definite. So this looks very complicated, but it can be written in this form below here as something quadratic in the dissipative currents. You just have to come here and look that all this blue stuff should be proportional to the bulk viscous pressure. Then this guy will be pi square. All this green stuff, all this garbage, has to be linear in n mu, and then this guy will be quadratic in n. And finally, the last term should be linear in pi mu, and so it will be quadratic in pi mu. So then this new ansatz will guarantee that your entropy is always positive definite, and you respect the second law of thermodynamics. If you do that, you will get the famous Israel-Stewart equations, which look way more complicated than the Navier-Stokes equations, right? So the first difference here is that you obtain something qualitatively new in the sense that these are dynamical equations. Yes? Mm-hmm.
Where did you get these conditions? I mean, in the previous slide.
Oops. So here, we're just trying
yes,
to...
when you say that it has to be proportional to pi...
why do I do this?
Yes.
Yeah, so essentially I want this thing above here to be positive definite. The right-hand side to be always positive. So we look for some... We know, I mean, Israel-Stewart, right? I mean, Israel-Stewart, they look for solutions like this here, where the first term has to be like pi square, so it's positive. The second term has to be minus n square, so be positive. And the third term, like pi square. So if you can do this, you guarantee that your entropy production is always positive, regardless of your configuration. And then if you look up here, if all of this blue stuff goes with pi, this is pi square.
Okay.
Right? Okay, it's true, right?
No, it's true. But I mean, it could be to the fourth.
It could be, yeah, but you want the, let's say, the simplest, the lowest order solution, yeah. You're right, it could be any even power. But here, just look for the lowest order. So the Navier-Stokes term...
And there's no other way that you get it if you don't impose it to be quadratic.
There's no other way, yeah. Of course, quadratic is the most simple and lowest order. Like in this case, it's always quadratic in the dissipative currents. That's the minimum order that you can apply. Yeah, that's the simplest thing. Even though it looks very complicated, this is the simplest thing you could do to
I mean,
ensure the second law.
what I mean is, that and I had this question before,
Yeah.
but I mean, if you have something linear,
Yeah.
but you have some cancellations or things like that, or maybe imposing that, I don't know, some expression must be larger than 0, then you get the whole thing larger than 0. So this would be another way to get it, right?
Yeah, so here, to have a cancellation, so the argument would be that if your theory is okay, the entropy should always be positive definite for any configuration possible. So of course yeah, exactly. So for instance, you can think of some fluid where, maybe this term cancels this one, right? And then it's positive. But you cannot, but it has to be for an arbitrary configuration. So this guarantees for any fluid that everything will be fine. Okay? And then if you do that, you get something like this very apparently complicated equation. And this equation here is dynamical in the sense that, so before we had a constitutive relation. So for example, Navier-Stokes would be the second term on the left equals the first term on the right. So this is Navier-Stokes theory, just these two terms. So your bulk viscous pressure is just proportional to the gradient velocity. Very simple. Now we have a dynamical equation for pi. So pi dot plus pi equals all of this. So pi is now a dynamical variable. It has to be given as initial condition. It evolves with time. So these are all dynamical equations for the dissipative current. This is a fundamental difference, right? This was not the case in Navier-Stokes theory. And if you want to just identify the variables, you have in blue the viscosity, so you can identify this omega pi and omega n and omega small pi as the inverse of the viscosity coefficients. And you can identify relaxation times in terms of these guys here. To make it simpler, let me write it this way. So now I throw away all the garbage. So this is the fundamental physics of these new equations. So we have essentially some time derivative of pi plus pi equal a Navier-Stokes type term plus corrections. So this is a theory that is relaxing exponentially towards this Navier-Stokes limit. And this is part of what you can understand as causality. So in this kind of theory, in Navier-Stokes, pi was just equal to minus zeta times theta. In this new theory, this will take some time to happen. So this equality doesn't happen instantaneously. So things have some inertia. The dissipative currents take some time to build up towards the gradients. Okay? It's a memory effect, as Gaston said in the audience. And this theory you can show not that it's causal and stable, but that it can be causal. So it's conditionally causal. So it will be a causal and stable theory as long as these relaxation times satisfy, for example, this condition here. This condition here is just for theories without any net charge. So the first and the third equations are applied. And you see that this zeta over this relaxation time plus eta over the relaxation time must be smaller than this number. This is 1 minus the velocity of sound squared. This is a condition for this theory to be causal. And what you can see already immediately is that if you take this relaxation time to 0, this condition is not satisfied. In other words, if you go to the Navier-Stokes limit, you become a causal again, and everything breaks down. So in Hertzian collisions, we always pick relaxation times which do not violate these causality conditions, okay? So this here is the theory that we solve in Hertzian collisions, or something like this, with all these three dots here. I think on the next slide, I show you what we actually solve. So this is the theories that we get from kinetic theory. So here we have everything with all the contributions. So we solve these equations, of course, numerically with using computers and so on. But what you can see is that we have a lot of unknowns here, right? So in Navier-Stokes, we just had one unknown. If I come back here, in Navier-Stokes, all that we need to know about the fluid was the viscosity. If we knew that, we in principle could solve it, at least in the relativistic regime. Now here, I already need all of these viscosities plus these relaxation times. I need to know more stuff about the fluid. And if we go to this next slide here, you have a bunch of transport coefficients that are also unknown, which kind of multiply some nonlinear term, which is just allowed by symmetry. So I think if you count, I counted once, maybe there are 20-something transport coefficients. 3 of them we care about, the viscosities. The relaxation times, we have to care a little bit because we cannot just put anything. It has to be causal. And all the rest is just things that most people don't even bother to think about. But if you solve this equation, you have to put something in. So I want to tell you, what do we put in? Yeah. It looks terrible. So here is what is solved in music. There's this simulation called music from the Canadians. And essentially in music, you solve these 2 equations just for bulk and shear. Nowadays, they are trying to add diffusion, but usually diffusion is just ignored. And here are the expressions for all of these transfer coefficients that are in music. Where do they come from? They just come from expressions from an ultra-relativistic gas. So we just say there's a very small mass over temperature, and you can calculate all of these expressions exactly in this way if you take the leading term. So either the shear viscosity over the relaxation time is the enthalpy over 5, and that's actually what is used in music, this number 5. Sometimes people turn this 5 into a free parameter and add it to the Bayesian analysis. But this guy here is 4/3, 10 over 7, 6 over 5. These are the kind of numbers that we put in music, and all the bulk ones are expressed in terms of the velocity of sound, and they have these simple expressions here. Yes? Ideal. Ideal, but small mass, almost m over t is small. Yeah. Now, what you should know from this is that this here is a very it's a very bad guess, right? I mean, it's very bad. I can say this because I did this, right? So I have the right to criticize it. So essentially, we have to put something in the code, and so we just gain some intuition from this very simplified limit, and then we added that. And what we do is we just say, okay, fine, this CS squared we replace by the QCD CS squared, the velocity of sound of QCD, and epsilon plus P, energy and pressure, we also replace by the QCD pressure, and we just use this for QCD. And then eta and zeta are just guessed from parametrizations. You extract them from the data, and everything else is given from these expressions. But the reality of the thing is, we don't know any of this, right? And these expressions could be actually incorrect by a large amount. So these are big unknowns, and you just cannot set them to 0. So that's the thing. Each of these terms, they don't have a very big importance in the simulation, but if you just set them all to 0, you'll see a difference. Right? So it's better to just keep something sensible than just set them to 0. But this is something that I want to emphasize today.
Could it be much larger?
Oh, yeah, yeah. One thing that we know for sure is wrong is the first one here. The zeta over tau pi, here is calculated as 15 times 1/3 minus CS squared, squared, and so on. This one appears to be not very realistic, and people are realizing it today because, yeah. So this is kind of a problem for us. Yes? Okay, so he asked why the diffusion is ignored, right? So usually we ignore diffusion because all of these things were originally constructed for very high energy collisions, and then you just produce so many particles from the vacuum that essentially the number of particles and antiparticles is the same. So we just approximate the net charge as 0, and thus the diffusion also as 0. So that's why people usually ignore the diffusion. But if you go to lower energy collisions, this is no longer a good approximation. Or even if you go to a high energy collision and you go to what we call large rapidity, it's also not a good approximation. So ideally, so some people are putting diffusion here, and then you have problems of guessing even more coefficients, right? It's a new set of problems. So just to discuss a little bit about the initial conditions. So these equations, they change a lot of things because now what we need to solve these equations are not only the initial values of energy density, net charge, if you have it, and velocity, you need also to provide the initial values for these dissipative currents. So you need to know more for your initial state. And that's very difficult, even more than before. So many models in heavy ion collisions, they just kind of ignore this problem. They just say, okay, fine, I mean, I believe these things are not very important anyway. I just set them to 0 initially and hope that doesn't matter. And many models, they just neglect this and the forward velocity. It's also very difficult to figure out what is the initial velocity of your fluid. So a lot of initial condition models, which is what I will discuss next, have to worry about understanding these things, right? So there any question about this so far, or should I go to initial condition? So I will do that. But I want to make a comment that this has to do with your group, which worries about magnetic fields. So one thing that some people worry about is how to take all of this and add a magnetic field, right? And this maybe I'll discuss a little bit tomorrow. So how do you take this kind of hydrodynamic theories, which are more complicated than Navier-Stokes, and you add a magnetic field and you construct a magneto-hydrodynamic equation, which is also causal. Because, of course, everyone knows how to do Navier-Stokes theory with magnetic field, but I don't think anyone knows how to do Isler-Stewart theory with a magnetic field. There are some initial guesses, but it could be way more complicated than we think. Okay, so should I discuss initial condition a little bit? And then you just cut me when you think we run out of time, okay? Yeah, because then I can still do this tomorrow anyway. Is it okay if I just do initial conditions tomorrow and open for questions now? Or?
Okay, yeah, that's fine.
Let's do it this way, yeah. If you don't mind, yeah.
Okay, so we decided to go to initial conditions tomorrow. So Gabriel already did a teaser of what's going to be talked tomorrow to attract all of you who are online. And we're now open for questions and discussions. No questions?
No questions.
Can you hear me? Nobody said that they can hear me. Hello? Oh, yeah, so they can hear me.
They just don't have questions.
Yes, they can hear me.
Can I ask through the Zoom meeting? Can I open my microphone and ask here, or it's better to write the question?
No, it's okay. We can hear you. The Zoom is connected to the speaker, so we can hear you. Go ahead.
Oh, okay. Thank you. No, if my master's project, it's about studying the P-led collisions. So I just didn't understand the P-led collisions. You cannot see very strong the anisotropy in the PT distribution. I didn't remember very much. If you could explain again this part, I would appreciate.
Okay, so you're asking about this anisotropy signals in small systems, right?
Exactly. Okay. It's a smaller system, so you said something about it being more hard to say that there is an anisotropy and there is a system of TGP matter being formed.
So actually, I mean, for small systems, the thing that you really do see clearly is exactly this anisotropy. That's why people think that there is a fluid there. So you look at small systems and all of these flow signals in the sense of V2, V3, V4, they are all there. With the caveat that, in principle, they are more strong for high multiplicity PA collisions, right? So we look at high multiplicity PA collisions, you see all of these flow signals also there. And that's why people think that you also have a medium there. So in principle, you do see everything there.
Okay.
But there is a problem which is in the sense that people cannot really measure this V2 directly. What they measure are two particle correlations. And then part of the V2 will come from like this kind of response to initial geometry. But part of this two-part correlation can also come from what people call known flow or intrinsic correlations between the particles. So when you have a small multiplicity, then it's very difficult to avoid these known flow corrections. And part of your V2 could come from some non-hydrodynamical signal. But for high multiplicity PA collisions, in principle, the signal is very clear. It's there. What I said in my talk is that it's harder to measure jet quenching and the thermal photon signal in small systems. That's what's more difficult to find. But this anisotropy is clearly there. And that's what motivates people to study with hydrodynamics. Did I answer your question?
Okay. Yes, perfect. Thank you. Thank you very much.
We have a question by Jordi Salinas. It's how is the existence of a CP handled in Heavian simulations? And the other question is, what observables are the ones that hydro models have more challenges with?
More challenges. So CP, I don't know if anyone has ever included this in a real hydrodynamic simulation. But when it comes to hydrodynamics, I mean, it essentially can describe everything that we try to describe. So of course, when you look at hydro, yeah, so I try to, everything is a lot, right? So it's too much. Wait. So here, we look at observables which are usually dominated by soft physics, like small PT physics. So if you go, of course, to high PT, nothing will be dominated by hydrodynamics. There's only one thing that I know that hydro cannot describe, is not described well, but not described at all, and this is called ultracentral collisions, which is very funny. So someone just asked me about small systems. So somehow, hydro simulations can describe small systems kind of well when it comes to this kind of azimuthal anisotropy and the transverse momentum spectra. So the small systems are covered. But when you go to the very large systems, hydro actually fails, and no one knows why. So by ultracentral means you really go to the extremely high multiplicity events and only look at them, and then hydro cannot describe the V2 coefficient and the V3 coefficient simultaneously. It just cannot. And I think no one really knows why. It's called...
Large, you mean high multiplicity?
Yes, high multiplicity. So you go to the events with 0.1% largest multiplicity or even more. And those events, they exhibit very strange behavior which we cannot describe with the current models. Even with Bayesian analysis, it's not possible. I don't know why. I worried about this long time ago. I couldn't solve it. No one could solve that I know. And it's still there. So this is the only thing that I know hydro has a tough time describing. Everything else is just details. I mean, if you look carefully enough and you look at V3, and you see that V3 is slightly under-predicted. This looks like a small matter here, but you have to remember these are the best simulations one can do, right? So it optimizes everything that we have. So, and then even then, V3 is a little bit not good. But this isn't something I worry about too much. But ultracentral is not a matter of fine-tuning. It's a matter of complete failure of describing it. Right, yeah. I can show a slide tomorrow just to make sure that you see the observable that I'm mentioning here. But, yeah.
So by CP handled, you mean like chiромagnetic effect or things like that?
That's what I understood. Was that did I understand right? I understood like a chiromagnetic effect, or...
Yeah, that's what I understood from it. He said CP handled, handled in equation of
yeah, you have
state.
To include this also in the discipline, like this chiral currents. This has been a problem because I don't know why, but the people who do chiромagnetic effect, they have never tried to implement it in a big simulation. And so there's always this expectation that somehow you can find a smoking gun from the data itself by doing some like isobar collision or like just preparing a very ideal situation where this observer would manifest itself. But in my experience, this never happens. Usually we need a model where you can actually fit the data in.
Yeah, but I mean, several years ago, people studied this in height. I mean, when we first had experimental evidence
Yeah.
of the chiromagnetic
Yes.
effect, or at least we thought we had,
Yeah.
then there were simulations that showed that fluctuations were enough to reproduce this data. So I think that,
Yes.
yeah,
And that's the problem. So there's a large signal which comes from flow, like V1,
yes,
which is
yes.
dominant.
I think that's the reason that we didn't have many simulations considering it later, because it was shown that the signal could be
But still,
washed.
you have
and
to try.
yeah.
I mean, you have to try to do something. Like otherwise, you're never going to be able to either exclude it or measure it.
Yeah, sure. I just understand that they were waiting for something new, experimentally speaking,
Yes.
something that could be separable
Exactly.
from other things. I mean, in the way it was, I think that people concluded many years ago that it was kind of useless to do simulations because the signal would be washed.
Yeah. I think I mean, I never seen a smoking gun in heavy ion physics to this day. Like something that you can really just measure and just extract something without any kind of modeling. It's very difficult. Like even when people did some time ago J-psi suppression, and then they found out, they thought it was a smoking gun for QGP because the medium would melt J-psi. But then you look, it was also there in hadronic transport, like when you did the simulation. So then you see, okay, it's not really a smoking gun as we thought. So usually, I don't know.
In this sense, nothing is. So we have
Yeah.
to work with something, right?
I think you have to really model this thing in the context of the hydro simulations and really try to understand what are the real effects on observables. Because it's actually quite difficult to compare to data. It's not easy to compare to data in a correct way, because you have to make sure that you're doing exactly what the experimentalists did when they calculated their observables, and for that you actually need a theory, a model which has the right fluctuations, everything there. So I don't know. CP violation.
No.
Huh?
And you never know if the right, I mean, if you're working with right fluctuate, what?
Yeah,
I mean,
you never
yeah.
know. Like even this net charge fluctuations that were for the chiromagnetic effect, which is essentially a correlation between if you have some decays, of course the plus and minus charges are correlated, right? And this is the correlation that is more trivial than the one induced by a magnetic field in the vacuum and so on. And this is dominant. Even that kind of correlation is hard to introduce in hydro models. Like to really do it event by event with the proper net charge conservation. Even that is hard to include.
Okay. So we have more questions. Why? So, Tiago, do you want to open the microphone? Or should I ask you?
Yes.
Oh, I can ask. Thank you, Gabriel. And why people usually analyze the linear causality condition using only the shear relaxation time without add the two relaxation time at the same time, as you show it in the slides?
Oh, so you mean why not do the combined like I
Yeah.
showed you? Oops. I'm trying to go there. Just a minute. This one, right? So of course, I think just because people either forget or they don't know. I mean, it's one or the other. So of course, when you have a theory with bulk and shear, this is the real causality condition. Of course, if you just have shear, this is the condition, just the second term is there. If you just have bulk, just the first term is there. But if you have both of them, you really have to do this complete condition here. And people have made this, maybe you're asking because you know this, but people have made this mistake already. So people who do Bayesian analysis, they usually restrict their parameters by just choosing relaxation times that are causal. And the mistake they made was that they did this one and this one independently. So of course, when you sum them, some of their prior parameters in the Bayesian analysis were acausal. And therefore, the results of the whole thing. Now, luckily, the heavy ion results usually unfavor acausal parameters, so that's, I guess, lucky of us. So these parameters are never selected as the best ones. But what my answer to is just a mistake. And if you add net charge diffusion, there will be another term here as well. So if you add diffusion, there will be a sum of 3 terms and some inequality that you have to satisfy. So one really has to be careful not to violate causality when you add more dissipative currents.
Any more questions? I have one more question. So you said in the beginning of your lecture that it is essential for things to work that you reach equilibrium very quickly. This was a conclusion in the beginning when people applied Navier-Stokes, and it remained in the same, I mean,
no,
in the same
they
way
never
when
applied Navier-Stokes. So it's always, so in these models, the initial time, the time where you start hydro is, let's say, a parameter. Nowadays, this is how you do it. There's some time where you just start
but you fit it.
Exactly, and you fit that to data and see what is the best time and so on. It's extracted because we don't know how to calculate it.
Yeah, my question is, in all the approaches you can apply, this is a consensus.
Yeah, it doesn't vary that much. This initial time to apply hydro is usually not above 2 Fermi over C. It's at largest 2 Fermi over C. So it's always like we start hydro around 1 Fermi over C, and some people start it sooner, some people start it later. It's just an unknown parameter.
But I mean is that, you cannot fit data if you don't consider this parameter being very small.
Yeah.
It's a condition for, all the valid approaches to have this small.
Exactly. And to be fair, I lied to all of you. So as far as we know, it doesn't thermalize. So in all simulations that we do, we never really see that the system approaches equilibrium. It's really kind of far out of equilibrium. It takes, even within the fluid stage, it takes a long time for it to approach, let's say, a situation where pi mu is actually small compared to the equilibrium part. But the thing is that as far as we checked, these hydro equations, they work even when the system is very far from equilibrium for some reason. They still appear to be applicable, at least as far as we have tested them. We test them, and we see that they are working. So people have kind of invented a term to parameterize our ignorance. They call it hydrodynamization. Because usually people would say, in order to apply hydro, you need thermalization, right? So the system thermalizes, and you can define a thermalization time. Now, of course, as far as we have checked, this is not happening. The system is not thermalizing very quickly. It's actually initially very far from equilibrium. But still, hydro appears to work. Then people call this hydrodynamization. And hydrodynamization is just, as I said, a term to parameterize our ignorance. It's just a hydrodynamization time is a time where hydro starts working. Why? I don't know. No one knows. So some people worry about just this problem, like, why is this system hydrodynamizing? I don't know the term. Why is hydro working? Yeah?
Cannot be one reason that you have to fit these coefficients, these transport coefficients, and they can be completely wrong. They have nothing to do with the fundamental theory, for example.
Yes, so this is for sure. So I don't know if they heard Gaston, but he's maybe asking that, of course, we have a model with many free parameters, and we are optimizing like these parameters to fit the data. And the question is, are these parameters that are extracted the real properties of QCD matter, or they're just part of some optimization procedure? The answer is that we don't know. So it could be that the shear viscosity is not the real shear viscosity, but some effective shear viscosity. And the same thing for the pressure and everything else. So in this sense, maybe we are failing at the original task that I started this talk, which is produce a system close to equilibrium and extract thermodynamic properties and transport properties. Maybe we're extracting things which are similar, but not exactly the same. Right? They are, because the system is not close to equilibrium. I think this is something that people have to take seriously at some point, that the system is not close to equilibrium, but somehow we can still derive a hydrodynamical theory somehow. But then you have to reinterpret the transport coefficients. So I know some people who, for example, think about expansions not around equilibrium, but around fixed points. And they also try to understand if you can have a hydrodynamical theory, not around the equilibrium, but around the fixed point. And funny enough, I mean, they often see that sometimes it works. Sometimes it looks like hydro, even though it shouldn't be. But the price you pay is that the transfer coefficients have to be reinterpreted. So this whole issue about understanding hydrodynamics and understanding hydrodynamization has to do with understanding what we extract from data. Is it the real shear viscosity, or is just some similar transfer coefficient, but of a far from equilibrium fluid? That's one possibility. But I emphasize, the party line is that this is close to equilibrium, that we have a fluid, and that we are studying the transfer coefficient of QCD matter. That's the official answer so far.
An effective transport coefficient is a transport coefficient, right?
Sure.
I mean,
sure. But then it wouldn't be the one from the Kubo formula that you calculate from QCD.
Yeah.
So in other words, maybe the shear viscosity is small, not because the QCD one is small, but because this effective one is small. That's a possibility that we cannot exclude. But of course, we can also not just believe in that per se, right? It has to be checked. So far, we believe we extract the viscosity of QCD matter, and that's that, right?
Okay.
Yeah. So this is being taped, right? I guess I said some
Yes.
things here that maybe don't.
Yes,
I don't
it's
look
being
very
recorded.
Good.
I hope
Yeah.
so. I hope
Oh,
they're
okay.
recording it there. So, do you have more questions? Yeah.
You showed 3 types of net charge.
Yes.
How does the electric charge and the strangeness charge appear on the hydrodynamical perspective?
So he asked about the 3 conserved charges, right? So in principle, because we believe that only the free light quarks thermalize, so the heavy ones, they wouldn't, even if they are produced, of course, but they won't thermalize with the medium. And that leads to 3 conserved charges. And in principle, you can write as electric charge, baryon number, and strangeness. So far, people have put a lot of effort in just adding one of them, which is the baryon number. I don't know if there are many simulations where they add all of the conserved charges. And I think Kevin is trying this, right, at USP, but yeah. So yeah, Jack is trying in Urbana. So some people are trying, but it's just difficult because, so at zero chemical potential, it's convenient because we know the pressure. So we got used to just running the simulation without worrying about the thermodynamics. We just worry about the transfer coefficients. We don't have to parameterize the pressure. As you go to, as you add more, as you consider non-vanishing conserved charges, you're just adding more degrees of freedom. And so first you have to worry about the pressure. How does the pressure depend on each of these charges? That's complicated enough. You know up to some level, but you don't know everything. Then you have to worry about all the dissipative currents that would emerge. So now you have more than 3 dissipative diffusion coefficients that you have to know. It's just so many unknowns that. And then the most important thing is you have to somehow figure out what is the observable that you measure that would be sensitive to this specific physics. Because otherwise you're just lost. I mean, you vary these things and everything vary together and you cannot really extract it. Even if the Bayesian analysis is complicated. But I think people are trying. Maybe it's easier in stars, I think, than in heavy ion collisions to consider these non-conserved charges and to do these other conserved charges and simulate them. But it's a complicated problem.
More questions? So if not, let's thank
Good.
Gabriel again.
Thank you.
Again, no, for the first time. And tomorrow we have the second lecture at the same time. And you already had the teaser that he'll talk about initial conditions. And this is a point that might be especially interesting for people interested in electromagnetic effects. So see you tomorrow.
Okay, thank you.
Bye.
Vou ter que tirar.